Yeah, I'm glad that I can continue a bit what Walter said or told you yesterday. I think he was talking mainly about TDEs and leaving the gamma ray burst. No? Okay.
Yes.
Not yet. Then this is going to come tomorrow. Okay, but anyways, I'm going to talk about GRBs and take at least part of that load. So let's briefly get an overview of what I will be talking about. So the main research question that I want you to have in mind is how we can interpret neutrino limits for a specific source type. And I will be focusing on how or whether we can constrain the amount of accelerated baryons in a specific gamma ray burst. Now, I know that a lot of you may not have heard about GRBs before, so we're going to start with a very brief introduction about GRBs. What are they? How do they work? What are the current neutrino limits? All of that. I will talk a bit more about the prompt emission models, because that's what I'm mostly working on, the prompt phase of the GRB. And then I wanted to show you one specific example of how we do the modeling of a GRB and how we use the neutrino constraints for that specific GRB to draw conclusions. Okay, GRBs. I don't know. Have you heard of it? Haven't you? Anyways, yes, maybe. A GRB happens if either two compact objects merge. So you have either two neutron stars or a black hole and a neutron star that expired in, merge, create a new central object. Or you have, in the case of, and then this is called a short GRB because it lasts less than 2 seconds. Or in the case of long GRBs, you have a very massive star that explodes at the end of its life. And again, it creates a new central object from the accretion disk and jet launching processes. From that central object, a jet is launched. And it's that jet actually that creates what we call the gamma ray burst. So you can see, oh, no, I need to. Oh. Here, you can see here at the left side, you have the new central compact object, and it has an accretion disk. Remember, for short GRBs, this also means that you need at least one neutron star, right? Because you need some material to form the accretion disk. You cannot have a short GRB from two black holes. You have an accretion disk, and then it launches a jet. And initially, that jet, it's very dense, very hot, and it's opaque to its own radiation. So nothing can come out. You wouldn't see anything. You can only observe any radiation from a G at a point that we call the photosphere, where the jet becomes optically thin to its own radiation. Remember, this is the first time we can see any light from this jet. Before that, nothing. Then the jet keeps expanding, and we have what we call the prompt emission. Somehow during the still expanding jet and interactions of the jet within itself, there is a very short energetic gamma ray burst that is created. And this is also what gives the name to the object, GRB, gamma ray burst. It's just a flash in gamma rays. At a certain point, the jet starts decelerating, and as the jet decelerates, it creates a long-lasting multi-wavelength signal. It goes down to KV, it goes down to X-rays, optical, and that part lasts weeks, even months sometimes, depending on how far and how energetic the burst is. In what I will be talking about now is the prompt emission. The afterglow is a completely different field to my view. At least typically it's other people who study it. Of course, something that is to be mentioned in GRBs is that it's not only a source of photons and of the phenomenon that I'm showing here, but also, for example, in the case of short GRB, where you have the in-spiral, you have a gravitational wave signal. You may have heard of that there was an association of a gravitational wave signal with a short GRB a few years back. And then also, of course, you have, in the case of short GRB, you have kilonova that is maybe produced on top, and long GRBs supernova. So the GRB is maybe accompanied by some other phenomena. Okay, but let's come back to the prompt emission. And let's talk about what you know about the Prompt emission, which is what it looks like. So the first thing that I want to tell you is that GRBs are one of the most energetic events in the universe. So they release as an isotropic equivalent. So if they were radiating in a whole sphere, something between 10 to the 49 and 10 to the 55 Earths. Of course, they are not emitting as a sphere. I just showed you before that we have a very narrowly beamed jet. We just typically quote the isotropic equivalent energies because we don't really know the opening angle. But it's typically very small, a few degrees, roughly. And overall, this is roughly the energy of a supernova that is released, but only during this very short gamma ray flash of a few seconds. So it's very, very energetic. Also, GRBs are not a local phenomenon, but they occur all over the universe, and we measure them in very, very large distances. Like the typical redshift is about 2, but I think the largest redshift that has been seen for a GRB is 8, which is really, really far away. One of the furthest objects ever seen. If we talk about how a GRB looks like in photons, we have 2 main observables. The first one is the light curve. Light curves just tell you how many photons do arrive as a function of time. And that's what you see here in this plot. So we have always on the x-axis the observed time, and on the y-axis the counts. And what you can see is the time distribution of photons, it's very different from event to event. You have some that are just one spike, others which have some short-term variability here, and not one looks like the other. So even though it's the same object, in terms of how many photons do I catch per second, they look very different. However, light curves is only one typical observable that we have. The other typical observable for photons that we have is the spectral energy distribution, or the spectrum. And the spectrum tells you how are the photons distributed in energy. So you have on the x-axis the energy now, of this sketch, obviously, you have the energy logarithmic, and then the number of photons per energy interval multiplied by E squared. You've seen that E squared representation before, right? So it just tells you in which energy band do I observe most photons. And the interesting thing about GRBs is that the spectrum looks very similar for all of the events. You have the peak here, which lies in the kV to MeV range. Below the peak, you have a spectral slope of roughly 1, so power law slope of roughly 1. Remember Walter telling you a straight line here in log-log. It means that it's actually a power law. And above the peak, you have a slope of minus 0.2. I'm also pointing out here, which is the energy range where we typically measure them, which is obviously around the peak, because there's just the most energy that is deposited, and we catch that, which is in the kV to MeV range. And the typical instruments are, for example, on board the Fermi satellite, we have Fermi GBM, and then some older ones. It is, however, also interesting to look at the multi-wavelength picture and to maybe go down to lower energies, so to X-ray, to optical, to UV, to use that as complementary information, or also to high energy and a very high energy regime. Okay, that was a lot about photons. We are not on a photon school though, right? So the question is, are GRBs actually neutrino sources? And of course, people have looked for it. No, they have just compared the catalog of known GRBs with the catalog of detected ice cube neutrinos. Of course, these are not all the ice cube neutrinos. I'm just using it as a representation. Yes. So basically for GRBs, you have 2 things, right? It's a transient source, so you have timing information, and of course, you also have some spatial information. Unfortunately, there was no association so far with any GRB that we've seen to any ice cube source that we know, ice cube neutrino that we have measured. What does that actually mean? Does that mean GRBs cannot produce any neutrinos? Well, it's not that easy, no. It actually just means that whatever neutrino production we have in GRBs, it must be lower than our current sensitivities of the instruments are. So in this nothing, if we express it more scientifically, it translates into upper limits of the fluence from a single burst. So for each burst, we know, okay, it cannot have produced more neutrinos than the sensitivity of ice cube for that specific event. And also we have upper limits on the diffuse neutrino flux. So for the population of known GRBs, this is the maximum flux that we can have. The interesting line to look at here is the combined analysis, which is the differential flux limit, and comes from the sensitivity of ice cube, basically. Yes. One word on the single source upper limits, which I will be talking about most also in this talk. These are most powerful for energetic events, simply because if you have more energy output for an event, it naturally, typically for a certain percentage of proton acceleration, also has a larger output in neutrinos. So you just, the expected number of, the predicted number of neutrinos is generally larger for very energetic events, which means then that the sensitivity is more powerful in constraining. Okay, but the main topic of the next 20 minutes, okay, I'm too slow, is to interpret these limits and to see what can we actually, what does that mean? What can we understand from it? In order to understand what they mean, unfortunately, we need to go a bit more into detail on how gamma ray bursts work. The main thing that is a bit difficult about GRBs is that we don't really know what generates the prompt emission. So how the photons, which mechanism generates them, and also how the energy dissipation works in the jet. What converts the kinetic energy of the jet into something that makes non-thermal radiation that we observe. And in principle, there are two categories of models, I would say. That is, first, the models in which the observed radiation, and in that sense, typically also the neutrinos, are produced below the photosphere. So when the jet is still opaque to its own radiation, and then it's released when it becomes optically thin. Now, GRB spectra are typically very narrow. They are not thermals though. So in order to explain the observations, we need some kind of dissipative process that would make the Planck thermal spectrum that you all know a bit wider and compatible with observations. On the other hand, it's possible that the radiation is not generated while the jet is optically thin, but instead optically thick, but instead while it's optically thin. In that case, we always think, or we typically think, that the observed non-thermal radiation comes from accelerated electrons. So I need some kind of mechanism in the jet that accelerates electrons, which then radiate and produce the photon spectrum and the photon counts that we observe. One possibility here is magnetic reconnection. So if even deep outside in the jet, you have non-negligible magnetic fields, which can invert field lines and so on, you could have magnetic reconnection, which by some different processes is able to accelerate particles. That's what that sketch here is supposed to show you, with the magnetic field lines and these magnetic islands, which typically for magnetic reconnection plays a role. The accelerated electrons, on the other hand, could also come from acceleration by internal shocks. Internal shocks, I will explain a bit more in detail later. Basically, you assume that in the jet, you have regions that move at different speeds, they collide, and this creates a shock. And I hope you listened very carefully to Enrico yesterday, who explained to you how at a shock you can have acceleration of non-thermal particles. A third possibility is, or not a third possibility, let's say it differently. There is, of course, also the possibility that you have both, right? No one tells you that it shouldn't shine when it becomes optically thin, and then later on also. So you could have a spectrum that is composed of more than one component. And so in any case, any of these models in principle should reproduce the electromagnetic observations, right? So you should always get the same type of spectrum that looks the same for all GRBs, and the light curve that is very spiky. An interesting question, I think, though, is how the different models would yield different neutrino predictions. And if we think about neutrino predictions, I want to point out one very basic thing, which is that neutrinos are produced in photohadronic interactions. So you have a population of protons interacting with a population of photons. And in principle, just how effective these interactions are depends very simply on the number density. So how dense is the medium for the photons and the protons? Number density, however, means number of particles just divided by the volume. And GRBs, we don't think of a sphere, we typically think of a shell. So you have the radius from the central engine squared that goes into it, and then somehow the co-moving width of the region. And this is really what could be different from model to model. So obviously, for example, for models that are connected to the photosphere, the dissipation radius is very small, right? So it would be a lot denser than for models which work in the optically thin regime. Then also what is different is the efficiency. So how much kinetic energy does the jet need in order to be to reproduce the observed photons, and how the jet is composed, how many baryons are reasonable to have, which part of the jet carries the most energy, do the magnetic fields carry most of the jet energy, or is it the thermal particles? Yes. And of course, depending on how the acceleration process works, so maybe if it's shock acceleration or whether it's magnetic reconnection acceleration, the spectrum of the accelerated particles would look different. Enrico yesterday told you that for shock acceleration, typically you would expect a spectrum of -2. This is, of course, different if you look at magnetic reconnection. The same is true for the equipartition parameters, like how much of the energy can go into acceleration of non-thermal protons versus non-thermal electrons. And this parameter here, by the way, we typically call the baryonic loading, and it's also what typically theorists try to constrain, like how much more protons am I accelerating compared to electrons. And why am I showing all these different parameters here? Well, because the number of particles, it's just the integral over the differential distribution of particles between Emin, Emax, and then you have the slope. So all of this together defines your number of particles. Now, at this point, something to not forget is the cooling of intermediates. So if you have very strong magnetic fields, your particles may cool before they decay into GNOs. So that can definitely impact your neutrino spectrum. And also here, I quote the total number of particles. Of course, for photohadronic interactions, you need particles which are energetic enough to participate in them. So you have a certain threshold effect. Okay, but in principle, we know that depending on the model, all these things may look different. So the number densities may be quite different. And in terms of neutrino predictions, this can be very nicely illustrated by a model that was in a paper that was recently published by my group here, where they just looked at the internal shock model, for example, and the magnetic dissipation model. And for each of the models, they took typical parameters of how the accelerated particle distribution would look like, where the dissipation would occur. And all these lines, you don't need to understand in detail. They're just here to illustrate. It depends a lot on the model. And until we haven't figured out the model, there is a large spread that we can have in the predictions, no? One last word to say about this is also that here they only assumed one dissipation region. But in reality, of course, as I told you before, you may have multiple emission regions, and especially like that is so-called multi-zone models, where you account for different emission regions along the jet. And again, in the context of neutrino predictions, this is super interesting because as you move out, the density drops, so the neutrino production becomes less efficient. And typically in these models, you decouple the production regions for different particle species. So you can see here, so we have the distance from the central end in here, and how much energy per radial interval is dissipated. We see that neutrinos, most of the energy that is emitted in neutrinos is emitted very close to the source where the densities are high, whereas in this case, whereas ultra-energy cosmic rays are emitted a bit further out, and gamma rays throughout the full zone. Okay, this was the background on what we currently know about neutrino limits and how difficult also they are to interpret. I want to take, say, 10 minutes, a bit slow, sorry, to illustrate how we do the modeling process for one specific GRB. And I took as an example here GRB 22109A, which happened last year. So just to give you a brief introduction why I took this GRB, that GRB was detected last October, and it was super spectacular because it was, I think, the most energetic GRB ever observed with 10 to the 55 Earths, and it was extremely close, a redshift of 0.15. That's rare to see in a GRB. And there was a paper, I think, which said that this combination of the proximity and the energy that was released, it's a 1 in a 10,000 years chance. So it kept the whole community quite excited. It was, of course, seen by all the major instruments and in all the wavelength bands. A funny thing to point out here is that, I mean, typically we build instruments for GRBs that are further away and fainter intrinsically. So we have very sensitive instruments. If something so energetic happens so close by, all the very sensitive instruments go into saturation. And all the typical instruments that we use for GRB detection, it happened, what you can see on the light curve plot here on the top, were here in the most energetic parts of time intervals of the burst, they were just overflooded and they were stopped detecting properly. So yeah. Unfortunately, there were no neutrinos. Marcus can tell you more about that. No and it also triggered some fun beyond the standard model physics ideas, because there was apparently an 18 TeV photon seen by LASSO. Now 18 TeV photon to survive, so what I'm plotting here on the bottom is the optical depth, the absorption coefficient due to EBL absorption as a function of energy. And you see that for an 18 TeV photon, we would be sitting here. So the absorption coefficient is super large, just due to propagation to Earth. And since the absorption coefficient and that energy was so large, a lot of people speculated that, well, maybe it could be beyond the standard model physics. I don't believe it. Don't believe them. Full stop. Anyways, so it was an interesting object, and it was very close to what we had been studying anyways. So the question that we had in our mind was, of course, can we model it, and what can we learn from neutrino constraints? Now, for that modeling process, I told you before there's some models that can be applied. Now we need to settle on one, no? Otherwise it becomes a bit difficult. And the model that I typically work in is the internal shock scenario. Now is actually the time to explain to you a bit more into detail how we do that. So the internal shock scenario is based on the idea that you have a plasma, a jet, which doesn't move uniformly. So you have regions that are faster and regions that are slower. And if you have a fast region of the jet, which is behind a slow region, eventually the fast region will catch up, and then you have a shock. And then at that shock, you can have particle acceleration, and so on and so on. But the main idea is that your jet has regions that are fast and some that are slow. Of course, in principle, you would need a full RMHD simulation of the jet to identify those regions. And but this is very computationally expensive. And what we typically do instead is we just slice the jet up. So you have the jet and you put it in slices, and each slice has a different velocity. And then you can just calculate when these slices would collide, how much energy would be released by energy conservation. And you can sum of all the contributions of these slices interacting, and that gives you your full signal. This is the internal shock model in very brief. And that's the model that we actually applied to model that GRB that I just told you about. So we took the observables from the GRB. So the light curve that was seen by some instruments. Here I'm showing one by an instrument that was not saturated because it's just not so sensitive, and typically we don't use it, but now we were super happy that it was there. And some preliminary analysis on how energetic it was in total and where the peak of the photon spectrum would lie. And then we kind of just guessed an initial distribution of these slices, because you need to have an initial guess of how they would be distributed in velocity, like which one would be fast, which one would be slow, and so on. And we, from that, we guessed that it could be looking like this, because out of experience, this would produce something like that. Typically, the initial distribution here will produce something that very similar in the light curve. And we, of course, also made some assumptions on how energetic was the jet at the beginning, what was the magnetic field, how do the accelerated particle spectra look like. One thing I wanted to point out here is how the average collision radius, which you may remember is very important for the densities, so for the neutrino production efficiency, how it scales. The first thing that it scales with is the average gamma. Obviously, if it moves faster, the collisions between the slices will happen further out. And then also the time variability. So if which is related to the how much are they apart. And typically larger time variability and larger Lorentz factor means everything happens a bit further out. Okay, from this initial Lorentz factor distribution, you can just calculate where each of the slices would be colliding, and that's what this thing is supposed to tell you. Each dot represents one slice colliding with another, and how that is distributed as a function of radius. And here is the energy transferred to thermal electrons, which is just a proxy of the total energy that is released. Once we know where the slices collide and how much energy is released in each collision, we can just, for each of these collisions between slices, calculate how many particles would be accelerated, how much radiation would be produced, how much radiation would be released. And summing over all of these little dots and their emission, we can then propagate it to Earth, obviously. And we can then see what the particle emission would look like. And you see here, the red is the result from our model, and the blue are the observations from the light curve that I showed you before. And you see we can nicely reproduce the time profile. Okay, but this is photons. Now, we wanted to talk a bit about neutrinos. For the neutrino limits, I'm not going to show the light curves, but instead the spectral energy distribution as before. So the number of particles as a function of energy. And we have that here. So you have in solid lines the photons, and in dotted lines the neutrinos, and this is just E squared dNdE, as you've seen before, as a function of energy. Just to point out briefly, there is two model assumptions that are a bit important. The first one is that here we put 3 times more energy into protons than into electrons, and of course the neutrino fluxes would scale with that, because it scales up your total number of protons. And also we have 2 assumptions on the magnetic fields, strong ones, which is synchrotron dominated, which here is called synchrotron dominated, and weak ones, which here is called inverse Compton dominated. It's a bit, there is many lines in this figure, so let's briefly go through all of them. First, the multi-wavelength predictions. So the solid lines, only photons. The first thing that we observe is below the peak, it's all quite similar. We only observe differences here in the left band. If we compare these predictions to what was actually observed, all of them are a bit too wide. So the actual observations, it's more narrow. So it would be a bit more, yeah, well, narrow. Unfortunately, I didn't find any set of parameters that could reproduce that. Too bad. Then one thing I also want to point out is that here, the thin, slightly transparent line, that is the intrinsic spectrum, whereas the solid line is the EBL corrected one. And you see that anything that here is above 10 to the 12th, so above a TeV roughly, is strongly suppressed because of interactions on the way to Earth. And the last thing that you cannot see, but you just have to believe me, is that there is basically no signatures of baryons in the photon spectra. Here, well, you might have actually guessed that, because typically you see here the neutrino spectra, and you know that photohydronic interactions don't only produce charged pions, they also produce neutral pions. And these neutral pions typically generate a peak that looks roughly like the neutrino peak, but is high energy photons. We don't see that here, not even in the thin transparent lines, which means that it's just a strong internal absorption in the source. Okay, lastly, neutrino predictions. Going to that, we see, first of all, the neutrino upper limit from IceCube that I put here as a straight line because it was quoted as an e to the minus power of -2 spectrum. We're below that. Even if I take the effective area and I integrate, I'm below the upper limit for neutrinos. That's nice. In that model, we don't violate. We can still have proton acceleration and put 3 times more energy into protons without violating neutrino limits. One thing I want to point out here is the neutrinos actually peak at a bit higher energies. So this connects slightly to Damiano's talk of tomorrow, who's going to be talking about radio array detection of neutrinos in a bit higher energies. Now, as last slide, you remember that, you may hopefully remember that neutrino fluxes and energies scale with 2 things, which is the baryonic loading. So if I put up the 3 to 30, I would also increase the neutrino fluxes by a factor of 10 typically, roughly. And also it depends on the dissipation radius. So if I play the same game and otherwise leave the parameters the same, but move the emission radius to 10 times more out, I move the neutrino peak to even higher energies, and I can fit even 30 times more proton energy in protons than into electrons, without generating a larger neutrino signal, because larger radius, the densities are lower, so I have less interactions of the protons, and the neutrino signal is typically weaker. Okay, and with that, I'm actually at the conclusions. We've been talking about neutrinos and GRBs. There are none. So we have limits for point sources and for the population, which are called stacking limits. The important thing is neutrino predictions depend on the density of the emitting region. And the tricky part in GRBs is that it's still not clear how they work. And in that sense, also the neutrino predictions depend very much on the model that you assume. What definitely is right, though, is that you may have to account for multiple emission regions along the jet with different densities, and this can decouple the production regions of different particle species. Then we went on briefly to talking about one very specific source, and I showed you how we modeled it and how we can interpret the neutrino limits for that specific source, where we saw that we do have consistency with the neutrino limits for some baryon acceleration. We cannot put it too high though, especially if we go to small radii. And neutrinos were somehow the only signature of the protons. We didn't see anything in the spectrum due to internal photon-photon absorption. Be aware, this internal photon-photon absorption, it can modify the spectrum at all energies. The cascade can be quite tricky. something that I didn't touch upon, but I think maybe Walter wanted to touch upon briefly tomorrow, is the connection to ultra-energy cosmic rays, if we could still have GRBs as the sources of ultra-energy cosmic rays.
And we have one question on Zoom. And I don't know, Simon, do you want to ask the question via microphone?
But how would we hear him?
Sorry, let me check if my it's actually possible. I can also read the question. Also, there was a question by no, no. Do you see the question? I can read it. Sorry. I must
No.
Okay, so Simone Costa asked, how can you identify if it is a GRB with light curves that are associated? According to the energy scale, is there any common characteristic to this kind of event?
Yes, I mean, you do identify it just by the peak, like the energy spectrum is very similar. The duration also is quite similar, right? We know that they last from the fraction of a second to roughly 10 seconds. Yes. And then also, of course, you have the afterglow, which is quite important. Typically, also the redshift the measurements and so on, they are done by the afterglows.
Somebody has that answer your question? Right, yes.
Okay.
Any other question? I don't see any on Zoom, but if there's any question, yes.
You mentioned that like a typical GRB distance is redshift 2, and
Yeah.
the boat was at 0.1 something,
Yeah.
and the kilonova was at 40 megaparsecs.
Yeah.
What do you think might be, and both of those were thought to be like once in a lifetime events?
Yeah,
and things,
yeah,
right?
yeah,
So
definitely.
odds on anything happening closer than that, what would be your gut feeling?
No, I mean, there is a subclass of GRBs that are typically observed a bit closer, which is low luminosity GRBs. For that, yes. For those also we have some, I mean, yes, okay, we've seen GRBs also closer than that, but not these, yeah, that
Not ones that would use neutrinos.
depends. Low luminosity GRBs have been discussed very much as sources of ultra-energy cosmic rays and neutrinos. And also, I mean, typically the GRBs that were seen by Hess and Magic in the very high energy regime, they were also kind of close now. Otherwise, you wouldn't see anything. Yeah.
Thanks.
So you don't want it to be too close.
No.
What happens if there's a GRB that is too close? It will destroy the ozone layer in the earth, and then
We might see things.
So I wanted to ask the light curve that you showed.
Mhm.
Very distinctly two, please.
Yeah.
What creates that?
It's a bit of a philosophical question. In our model, it's just very distinct regions of the jet where you have fast and the slow region, and they have to be emitted by the central object in kind of that shape.
Okay.
Yeah, but how?
So, you know, some of it arrives like something here, or they go to.
Yeah, I mean, just I think a jet that is emitted from some sort of central object, or not emitted, that is generated in the vicinity of a central object, and the mass inflow may not be steady, and the whole process may just not be a steady process, and it could just be that first in the jet there is a chunk of matter which is ejected, which is not so fast, and then you have a larger chunk which is faster, and within those chunks, of course, you have some variability in how the velocity looks like.
Specific for this one, then it's not like
No, I wouldn't say it's specific for that one. You have that behavior for like these multiple peaks with some short time variability on top. You have that quite often, but there is not a general pattern, I would say.
But if I understand correctly, you actually reproduce with your simulation the light curve.
Yeah.
You also have this
Yeah.
peak. But a
Because
different simulation might get like
a different simulation might get a different thing, but also our simulation would not be the only one that produces that. Yeah, and it's just typically, well, the initial Lorentz factor distribution is quite similar to what you get as a light curve. And you can just, I mean, knowing how broad the peak is, you know how big the regions would need to be, because it directly reflects one another.
Thanks.
What you called F is actually the 1/f that Walter had yesterday, right? Because, yeah.
So it's like a matter of nomenclature. So I tried in my slides to use like 1/f all the time. Or it's sometimes also beta. I mean, they're probably only moving money.
Ah, yes.
The main difference, actually, I mean, one thing which may not be so clear is that you use the ratio between electrons and photons. One is the ratio between gamma rays.
But yes, but the thing is, typically, it's the electrons that are, if you come from a particle acceleration point of view, your particle acceleration theory or modeling gives you how much more electrons are accelerated with respect to protons. And the gamma rays are then just the product of the electrons typically.
So for ICRC next week, I see this possible having proceedings where we also do internally some studies of the upper limits on this one F or F. So I think
exactly.
I guess share this in company to see what this will be public next.
Yeah, nice. That would be interesting.
I will see. Question. Let's take Annika again.
Thank you.